So half-life is simply the time taken by radioactive source to decay by half of its original value or amount. You see, the key point is that this is the time taken for that source. Since all unstable nuclei are always decaying in terms of alpha, beta, and gamma, they will end up becoming something else, and we've established that in the decay equations. We know that, for example, if uranium decays by alpha decay, it becomes something else with 231 and 90, 235 and 92. This is an entirely different element. So this is radioactive. X probably is also radioactive, but this has become something else. So we will call this as our parent particle and this as our daughter particle. Now, what is happening with the atoms? You see, for the sake of example, let's say that we have a sample and the sample contains 1000 atoms of uranium, right? Now, it is decaying to become X. Whatever X is, that's not our concern. We're not supposed to look it up in the periodic table. Whatever that may be, it's not our concern, right? So, if it is disintegrating to become X, then there will come a time where out of 1000 atoms of uranium, only 500 atoms of uranium will be left, and 500 of them would have become X, right? So this time that has passed by, while the atoms or the count of the atoms was reducing up to 500, whatever time has passed by, that time is known as half-life, and that is represented as capital T with 1 over 2 as a sub-letter fix, right? So let's go through that one more time. So for the sake of example, we have another element, we have another radioactive substance that has, for example, in its sample, there are 2000 atoms. So he tells us that the half-life or one half-life is at least 10 days, which would mean that if it disintegrates, keeps on disintegrating, let's say, first we find out that there are only 1800 elements left, then 1600, then probably after some time 1400, then let's say 1250, then let's say 1150, and then let's say it ends up with 1000. When it reaches 1000 atoms, the time taken from 2000 to reach 1000 will actually be the first half-life. And in our experience or experiment, that is 10 days, right? So although it is decaying, it is reducing its amount bit by bit with the passage of time, starting from 2000, it will undergo all the numbers as well. It's not that it's going to start at 2000 atoms and directly jump to 1000. No, it will undergo all these numbers because it is disintegrating one by one, right? So the moment it reaches its half point, where the number of atoms are left half the amount of the original, we have given that time a special name as half-life. That is all. So I will skip all of these central values in my calculations and just simply work with 2000 and 1000 because I know this is my final stop. So if he asks me the number of atoms left after 30 days, right? So I know that one half-life is worth 10 days. He's asking me the time frame after 30 days. So first, what I will do is find the number of half-lives needed. So my total time is 30 days. My one half-life is worth 10 days. So my answer comes out as 3. 3 half-lives will go by and I will reach my final destination, which he's asking me that how many atoms are left after 30 days. Which would mean that if I use the GM tube today, GM tube today, I get a reading of 2000. Okay, fine. Now I wait for 1 month, 30 days, and I place the GM tube again. What would I see on the GM tube? So let's try to solve this question. Let's try to solve it. So I start with 2000 atoms. I go towards 1000 atoms. Again, I repeat, there will be multiple stages between them. There will be. We are not concerned with that. We're concerned with the very first time we see half the value of atoms. So I will skip all the central stages and land directly to 1000. And this thing actually took 10 days to occur. So this is my first half-life. Then the next half-life, which will be 500. Why? Because that will be the half of this, right? So I am deliberately dividing these values by 2 to get the next atoms or the number of atoms. Similarly, this will be again 10 days. Half-life's value does not change. So even the next half-life will take 10 days. So this will be my second half-life. So by this time, I have covered approximately 20 days. I am 20 days into my experiment. But the question said that I want to find the value for 30 days, right? So I go back and halve it one more time to get the next value, which is 250. So this will again take 10 days. The value of half-life does not change. So this is my third half-life. Now let's notice what does this tell us. You see, the third half-life or the value third is what we found previously. So basically, this method that we've done actually tells us our stopping criteria. It tells us our stopping criteria. When do we stop decreasing or dividing this value by 2? When are we going to stop? Similarly, what some students try to remember it by is that if we found 3 half-lives, then we will see 3 arrows in our method. You see, if I count the number of arrows, this is my first arrow, which I use to halve. This is my first arrow, this is my second arrow, and this is my third arrow. So I'm sharing all the techniques and tips with you. No matter what you remember, no matter how you solve it, it's your choice. Again, now let's count from the very beginning to the end of our experiment. So the 30 days has gone by, and if I had tested the value today, that would have been, let's say, from the GM tube, that would have been 2000 counts per minute or radiation level, right? If I waited for 30 days and checked the sample's value again, then on my GM tube, I would have found this value to be 250, right? So if we try to plot this on a decay curve, this is what it looks like. So the time for each half-life will be the same, and you will see that's t slash days or number of days, right? And this will be your starting amount. This is 2000. This is 1000. This is 500. And this is approximately 250. So you will see these coordinates at specific locations. This is where we start the experiment. So at 0 days, today, right now. Then after first half-life, which is 10 days, second half-life, which is 20 days, then third half-life, which is 30 days. He can write this down as this configuration, or he may write this down as 10 days, 20 days, or 30 days. Doesn't matter. We must understand all the writing expressions. So the starting amount is going to be at 0, and then we locate the rest of the amounts. So my first half-life was at this location. After the first half-life, this was my current situation. After the second half-life, I found that 500 is the number of atoms that we are left with. And after the third half-life, we found that the number of atoms we are left with are 250, right? So if I draw a solid line curve through these points, I'm not going to draw a solid line because these coordinates will be cut out from them. I'm going to draw a line in which these coordinates are visible at least, and so on. So if you look at the trend, it looks something like this. The trend is something like this. This is also known as an exponential decay curve in terms of mathematics, purely mathematics, right? But point to be noted, this is my parent. The parent has decayed into reducing itself and becoming something else. What has happened with the daughter? You see, if I take it in this way, that this is my parent and this is my daughter, so the parent particles were 2000 at the beginning, but no daughter particles, no byproducts at the very beginning of the experiment. The parent particle reduced by half and became 1000 atoms. Where did those rest of the 1000 atoms go? They actually become the daughter particles. 1000 of them actually became the daughter particles. Okay, next stage. So they half again and become 500, right? So where did the 500 atoms go? They became a part of the daughter particles. So 1000 plus 500 will become 1500. So this was my time zero. This is my first half-life. This is my second half-life. So after the second half-life, my parent has gone from 2000 to 500, but the daughter particles have increased from 0 to 1500. Similarly, they reduce again by 250 by the third half-life, and I see that out of this 500, 250 have been converted into parent or are still left from the parent, and 250 of them have converted into becoming a daughter or a daughter particle or byproduct. So this will become 1750. So the purpose of doing this is one thing and one thing only, and that is to realize that the number of atoms at every stage still have remained the same. So the total number of particles in the system remain the same. You see, no matter from what point onwards and so on, if I add 2000 with 0, I get the total particles as 2000. 1000 plus 1000, 2000. With 500, 1500, 2000. 250, 750, 2000. Right? So the total number of particles in a sample, of course, the radioactive sample that we're talking about, are going to remain the same. If there were 2000 atoms or the radiation level was 2000, then it will still remain, at least in the number of quantity, the they will remain the same, right? Okay, so let's move back. We draw the graph of the parent because it is losing its values, it's losing radiation, and is reducing itself to become, of course, approaching zero eventually. But how does the daughter graph come into being? See, it starts from zero, and after first half-life, we see that the daughter particle observes a value of 1000. After this, the daughter particle observes a value of 1500 at the second half-life. So we see for the second half-life the value being this. So its graph goes over here. Then after some time we see it to be 1750 by third half-life. So by third half-life we see the daughter's value rise up to this coordinate over here. And again, this will be a smooth curve like this one, but I'm drawing them separately so that you can see individual coordinates, right? This will be a smooth graph always a smooth graph. So this is what's actually happening at the back end in terms of parent and in terms of daughter. We have drawn both of them. We have drawn a decay curve because the graph or the question may come in terms of, the question may come in terms of a graph. Not our problem, not our concern with that. The values will be given to you. You can simply backtrack your way to find out the half value, and then you can find out that, all right, this should have been the half-life, and that will remain the same for the rest of the question as well. So this is how half-life works, and let's look at another method of half-life in which he can give you different, the question will remain the same, but he will ask you, or he can give you different scenarios or situations for that. Let's look into that. Just a moment. Okay, so another situation he gives us that find out fraction of atoms left after 20 days if half-life is 5 days. Okay, no problem. In this question, not even the atoms are given to us. That what are the starting atoms, what are the ending atoms, nothing is given. But we do have the half-lives. So first, I calculate the number of half-lives by simply taking my total time space that I have. How much space do I have? I have a time space of 20 days. I can wait for this for 20 days. And every half-life is going to take away a chunk of 5 days from the system. So I'll have approximately 4 half-lives. And to put it in plain perspective, or for a very short trick, it will have 4 arrows in my experiment or in my question. So since he's talking about a fraction and no atoms are given, I'll have to assume the fraction. And I can do that in two ways. You will see this in two ways in the questions as well. So either you can assume the starting amount to be n, or you can assume the starting amount to be 1. So this is purely based on assumption. Assume the value to be n or 1. So the next step would be n by 2, then n by 4, then n by 8, and then n by 16. You see, let's count the number of arrows that we've taken. We've taken 1, 2, 3, 4, similar to the number of half-lives. Again, let's count the number of days and see whether we are getting 20 days or not. So it takes 5 days for the first half-life, 5 days for the second one, 5 days for the third one, and 5 days for the fourth one. Let's count all of them together. 5 plus 5 plus 5 plus 5 gives us 20 days. So we have successfully met the criteria, and I'm not over exceeding or I'm not under reporting the value of the time frame that has passed by, right? The other method sometimes you will see in MCQ's answers, or at least in the marking scheme of P2 question, is this one, that he assumes the starting amount to be 1. In terms of course, the percentage that, let's assume that at the very beginning, there were 100% atoms of the parent particle, right? So again, you will see the same fraction as 1 over 2, then 1 over 4, then 1 over 8, and then eventually 1 over 16. Same procedure, 5 days, 5 days, 5 days, and 5 days. Again, for the sake of your own satisfaction and checking the question again, you can count these half-lives again, and you will find out that this is 20 days, right? Okay, so how to write down the answer of this question? You will, if this is an MCQ, you will see a few options in the question. You will see options, let's say A, B, C, and D. And if it's a P2 question, we will write that as well. So in option A, he will tell you that the number of atoms are n divided by 20, or n divided by 10, or n divided by 8, or n slash 16. Alternative to these examples, you will see as 1 over 20, 1 over 17, probably, of course, I'm just assuming the examples, 1 over 8, or 1 over 16. So we know that even if we are starting with an assumption of n or 1, the last amount that we had was 1 over 16, or n by 16. So I will choose option D for my P1 questions. And if I had to write down a P2 answer, then I would write down that after 20 days, there are only 1/16th atoms left of parent after the decay process. So mentioning this as 1/16th or n by 16th would be your answer. And sometimes you will have to take in the examples in which he will himself mention that for the sake of example that the initial amount of atoms, or let the initial amount of atoms be n. So then you'll have to use that letter for your answer. If he doesn't do that, then you can simply start with the one example and go on as long as he wants you to end the question at whatever stage he wants you, right? So this is our half-life, and you will see this method in the book as well, that the notes that I've shared with you. This is how he actually follows that. So n by 2, then n by 4, and n by 8. This is the third half-life, right? And this is the graph that we just did over here for the parent and the daughter, this graph that you will see in the book as well over here. And similarly, let me draw the graph. This is for the parent, right? And this graph will be for the daughter. Of course, parent never becomes 0 and daughter never becomes 100. This is an ever decreasing process, ever decreasing, because the total number of atoms will never become 0. Eventually, they will one day, but we haven't tested it just yet. Okay, now let's try to do an example over here. He says that a radioactive element has a half-life of 40 minutes. The initial count rate was 1000. Okay, so we have a starting amount, 1000. How long does it take for the count rate to drop to 250 per minute? Now, this is my ending criteria. I have to decrease it myself by reducing it by half myself, right? Because I have the starting point and the ending point, but I don't know the number of half-lives it will take me to do that. So I see one half process or one halving takes 40 minutes, 40 minutes. So the total time it takes for this process would be 80 minutes. Similarly, if we go up to 125, I'll have to take this one step further to end up at 125, which will add 40 minutes more to the system and it will become 120 minutes. So the answer for part A will be 80 minutes, part A, and part B will be approximately 120 minutes, which he has written down as hours. Doesn't matter, right? So I hope that you understand the question and we understand that it's approximately very simple to see that. And similarly, if we ask you to plot the graph, we can do that. If we started with 1000, we will find the coordinate at 500, then we will find a coordinate at 250 and 125. But be advised that notice that the time interval between every half-life is the same. It will always be the same. So when you do plot these graphs, you will find out the graph actually has a curved pattern downwards, and mathematically this is known as an exponential decay curve. Purely mathematical term this is. And one more thing that I would like to add here is that we remember that radioactive process was random in nature. So there was reading fluctuation or fluctuations in the reading that we were getting on the GM2. In reality, if you take a sample or if you take the measurements from this radioactive sample, what you will end up seeing on the graph or eventually on the CRO or on the GM tube is that it is never going to be a smooth curve like this. This will always be fluctuating like this. Readings are sometimes more, sometimes less, sometimes more, less, more, less. But the general trend of the graph will be downwards eventually. And why is this happening? It's happening because the radioactive decay is a random process. Sometimes the number of atoms decaying will be slightly higher than what are supposed to decay, and sometimes they will be slightly less than what are supposed to decay, right? Uh, that is how it's going to take place. Because let's discuss this. Why is that? So 125. Let's discuss 125 half to the next stage. That will become 62.5. Is it possible to decay zero point 0.5 of an atom? Is it possible that half the atom decays and half does not? No, it's not. So to compensate for this, what happens is that spontaneously, again, randomly, it will be, let's say, that in some stages, 63 atoms will decay, and probably in the very next stage, only 60 may decay. So there will never be half an atom. Sometimes it will be overcompensated, sometimes it will be undercompensated. So this slight change in values will show up like this. Sometimes more, sometimes less, sometimes more, sometimes less. And eventually the average trend will be going downwards. So we are working with an average value, not with the random values, because it will become very hectic and inconvenient for us, right? So this is our half-life.